Hi, welcome to the second lab of the Serverless ML course. In this lab we're going to build feature pipelines for the credit card fraud prediction problem that we're going to work with in the rest of the course. So in this lab we're going to cover building the feature pipelines for writing features to the feature store for the credit card fraud prediction problem. We're going to have two pipelines, a backfill feature pipeline and then a synthetic data feature pipeline that's going to take synthetic credit card transactions, profiles, and it's going to write them to the feature store. So what we're going to do is we're going to take the common feature logic that's used by both of these Python notebooks, they're actually both notebooks, and we're going to put it into a Python package called SML, Serverless Machine Learning. And there's two Python modules in there, one for actually doing the synthetic data generation, and another one for returning back the features to the notebooks. So these are going to run as GitHub actions, and we also have some existing historical data as CSV files. So that's basically what we're going to build, and we're going to go through it step by step in this lab. So the first part is to get lab 2 from the course repo in GitHub. So I assume that you've already forked the Serverless ML course. If you haven't, you can go back to lab 1 where we show you how to fork our GitHub repo into your account. Assuming you have it forked, what you can do then is you can basically pull the latest changes, because we're releasing these notebooks once a week. So here I am in my account here, it's git remote -v. You can see it's Jim Dowling, serverless course. You can see I've only got this origin here. So what I want to do is I want to add a remote, and in this case I want to add this particular remote, which is the course remote. Okay, so let's go back. So I'm going to figure out where that is. It's available somewhere here. Let's kill this. I don't have this and this. Let's have a look. Where are we? Okay, so I'm gonna open up the GitHub repo. This is it. So this is the repo for the course, and I'm gonna get a reference to the here. We've got a reference to the repo, the HTTPS reference. That's fine. And what I can do is I can basically say git remote add, and then you give it a name. And one of the conventions is to call it upstream. Upstream means that this is the repo that your forked repo came from. So it's the upstream one. It's the original one, and you can pull any changes to your repo, which is downstream of this upstream one. So git remote add upstream this, and then we do git remote -v. We can see that, oh, I've got both origin and upstream as repos that I can access. So I can actually now call git pull upstream main, and it'll pull in the changes that have happened in the parent or upstream repo recently. Now, that's the first step. So you do that to get the notebooks and also the Python libraries that we're going to work with. One thing that I will point out is that you should document all of your shared Python modules. So in this case, the documentation is lacking, I would say. So I just want to highlight this point, though. It's very important that when you write, for example, Python functions in a module that's going to be shared by different notebooks, that people can go to those functions and they can easily read the name of it, the parameters, understand what the function does, and tells you what the return values are. So this is the standard way in which you would document any shared Python modules. So if we go and look at the code that we have here, and this is where we're back here, we go to source, this is module 02. We can see that we have two notebooks. We've got the backfill one, and we've got the prod or synthetic data pipeline. This is the one that we're going to run with GitHub Actions. It's going to run on a schedule. It's going to create some new credit card transactions. It's going to write them to the feature store, and the backfill one we run on demand. It's going to access the CSV files which contain the historical data. But you can see we have a couple of other folders here. We have scripts. This is the same one as we had in the first lab. We have a script to run this pipeline from a GitHub action, and this script is very simple. It just basically runs Jupyter NB convert and executes the notebook. So it's going to execute from the first cell to the last cell. And then we have this SML and test SML. So SML is our Python package, and it contains two Python modules. We'll also see that we have a unit test in here. So there's only a simple unit test in here for this SML, for in fact a function in one of the modules in this SML package. So remember, the package is the directory and the modules here are the files. So here we can see the shared files These are our Python modules. One is to create synthetic data. We can have a quick look at it. It's based primarily on this library called Faker. So Faker is a pretty useful library for creating synthetic data. You can just pip install it. So we've added it to the requirements.txt file in the base of the repo. So when you're under GitHub Action, that will also get installed, pip installed when it creates the container before it runs your Python program in the GitHub Action. You see here we've got a Faker object here. These are the parameters that you can tune for the synthetic data. So remember, we're creating credit card transactions for users. Those users have a profile. They also have the credit cards themselves. And you can see we've got a total number of users that you want to like to create transactions for. The number of transactions you want to create. The cash withdrawal cards totals. This is total unique cash withdrawals. ATM withdrawal sequence length. So how many times in a row do you take out money. The normal ATM radius, so the distance between them, and then start date and end date for when the transactions happen. And you can configure, and then the date format. You can configure any of these. There's more sophisticated parameters here related to the amount of money withdrawn. So you can see, or spent on the card. So you can see that, a lot of it's between 10 and 100 bucks. 50% of the transactions are, and slightly over, I think 35% is over $100. So each credit card transaction, when you spend money, the money will belong to one of these different categories. There probably should be something like an other category as well, a catch-all for things that are outside of this category, but that's an improvement you could make to this model. Remember, it's just a synthetic data module that we wrote for this course. In particular, David wrote this to simulate credit card payments. So there's an important parameter here, the fraud ratio, the percentage of transactions that are fraudulent. You could draw from a random distribution here to make it a little bit more realistic when it's running as a feature pipeline, but when you're testing, it's often good to have a fixed number here so that it's easier to then understand what's going on in your pipelines and reproduce the training data for your models. Number of fraudulent transactions is you take the fraud ratio, total number of transactions, and then you get the total number of fraudulent transactions. And we can see we've got attack chain length. So we said in the lecture that there's a couple of different types of attacks we're going to try and model with this synthetic data. One is small frequent credit card payments, which are called attack chains, and then geographic attacks, where we have two credit card transactions happen that are very far apart, and it's not physically possible to have the card in both locations at the times reported. You can see here it then says susceptible card distribution by age, so we're taking the person's age into consideration as to whether it's higher risk for fraud or not. And that's one of the features we had, which was the age of the user at the time they used the credit card. So that might, based on this synthetic data model, then that will have some signal as to whether it's slightly higher risk of fraud or slightly lower risk of fraud, depending on the user's age. So there's a bunch of functions here, and you can see they're not documented, like I said, but what we have done, in fact, is we've added the type information. So you can see that the parameter here, generate a unique number of credit card numbers, we pass in n, it's an int, and we return a series, a pandas series. And we're using credit cards. So sort of the Faker library has in fact a credit card function where you tell it it's Visa or MasterCard, and it will return back to your credit card number. So here we're just going to create a series of these credit card numbers, and it's going to be a list that we create a series from and return it back. We can get a list of credit card numbers, and you can see here then it's going to use the number of unique users and then the start date, end time, and so on to create these unique credit card numbers. So this is kind of a wrapper around the previous function. And we can I mentioned that we're going to use some unit tests for these functions because these functions are effectively APIs and they provide a contract. So if you break that contract, like if you introduce a new type of credit card here that maybe hasn't existed before, and it has a different type of number, well, that's going to break any downstream clients that are depending on those credit card numbers. So you have unit tests introduced to make sure that if someone makes that change in the code here, they'll get warned and say, well, your unit test failed for this credit card number because clients expect the credit card number to look like this with 16 digits. And if yours doesn't, you're breaking the assumptions or the contract that API provides. So that's why we do unit testing for feature logic in general. So you can see we have more methods. Generate a data frame with profiles. Remember, the profiles are the information about the owner of the card holder. We have also generate timestamps, generate random transaction amount, the amount of money spent on the card, generate a batch of amounts, generate a batch of categories for each amount. Each transaction will have a unique ID. That ID is actually not used when you're training, and the credit card number is in our data model. We had the credit card number and the timestamp, so the date time column for the for example, for the transaction event. That was our primary key, effectively. The entity ID is the credit card number, and we can uniquely identify each row with the credit card number and the date time. Now, what you ask yourself, well, why do I need a TID, a unique transaction ID as well? Well, in fact, in a real system, that unique transaction ID will be the primary key that's used for things like, when a transaction has been marked as fraudulent by somebody in a different organization, potentially, the people who are investigating fraud within a bank, for example, they'll mark that particular transaction ID as saying this is fraudulent. Then later on, you'll have two tables. You'll have the original transactions with a TID as a unique identifier, and you have this other table which has the outcomes, so the transactions that are marked as fraudulent. And you can join them together with this TID, which will be a common unique identifier across both of them. So we have another function here to wrap all of this together, to generate transactions and to generate cash amounts and to generate these chains of attacks. Individual withdrawals are there, and generate susceptible cards, normal ATM withdrawals, timestamps for fraudulent attacks, because we're going to simulate a fraudulent attack and the amount of money for a fraudulent attack, and then we can basically take in a list of transactions and chains and update them to make them either fraudulent or normal. And we can, so in this case, we're updating the normal ones, and here we can update then the fraudulent ones. We're going to return the data as a data frame, so we have some wrapper functions at the end for returning these lists as data frames. And that's basically the synthetic data module. The credit card features module is, it's at a higher level of abstraction. So you can see we're passing in now as parameters data frames. So we're passing in remember we have three data frames here. We have the transaction data frame, we have the profile data frame, and the user data frame. Sorry, the credit card data frame. So we have the transactions, the profiles, and the credit card. And this is what we covered in the lecture. It's our data model. And at this high level, we pass in the data frame, and you can see here it's basically calculating the card owner age using the birth date of the owner of the card, and then the current date time. So and that gives us back this new feature called age at transaction. We have another feature that we want to add called days until the card expires, and we compute that using the credit card expiry date and then the current date time. So the next feature that we have here is a complicated one. It's called haversine distance, and this is used to help give us predictive information for geographic attacks. So given the longitude and latitude of a current transaction and the longitude and latitude of the previous transaction for this card, we can compute return this value C, and C in this case is the haversine distance between these two points of longitude and latitude. And we also compute the time between the previous transaction and the current transaction, and together these two pieces of information, the haversine distance and the time delta between them, will give us enough information to predict if a card is a geographically, if a particular transaction is a geographic attack or not. There's a little bit more here, functions related to the just helper functions, and the activity level on a card gets computed. and we can do some of our aggregate activity by hour. So we said in the lecture as well, we're going to compute aggregates over the cards. So, we have a window length here, and we're using 4 hours as the window length. We're passing in a transaction data frame with the transactions. So what we're going to do is compute over a 4-hour window period of time. You can see we're using this rolling method in Pandas, and this will give us the rolling window, compute the rolling window of 4 hours. We're saying that the date time is the index on this transaction data frame that we're going to use, because we need to supply that with rolling windows. We're going to group by the credit card number, and now we're going to get back a data frame cc_group that we can go ahead and use to compute some of the different aggregation functions over this rolling window that are provided by Pandas. So we can see the first one we can cover here is df moving average, and what we do is we basically we're going to take the transaction. We're going to compute 2 columns called transaction volume moving average. So what we get back is a CC group data frame, and we can use that data frame to apply some of the aggregation functions that are available in Pandas over rolling windows. So in the first case, you can see here what we can do is we can create a data frame where we compute the mean over the CC group column, so CC number, amount, and date time, and we get back the data frame we call moving average, and then basically we can play around with this a little bit, and this is going to be our data frame that computes the moving average over these 3 features. And we don't need all of them. We don't need the moving average of the credit card number or the date time, so we only need it for the volume amount, and that's the one that will return. And we can do the same then for the standard deviation. We can compute the mean over the data frame again, and then in this case, it's gonna compute the standard deviation over it, and then we can also compute the moving average of transaction frequency, so the number of transactions within this time window, 4 hours. We can also compute the moving average of the location difference between consecutive transactions. So maybe 2 transactions are close together and the third one's far apart, and we're going to get the mean over all of those consecutive transactions. So what we'll get back is this window ags underscore data frame, and this will contain all of those features that we need. So these we can see the moving average of transaction volume, moving standard deviation of transaction volume, moving average of transaction frequency, and moving average of location difference between consecutive transactions. They're going to be in window ags df, and that's the second feature group that we're going to create. So let's have a look at how they're used, and we're going to start with the backfill example. And before I do that, let's just jump back to the instructions that we had in the lab. So the first instruction is to run this backfill pipeline, and then we're going to check in Hopsworks to make sure 2 feature groups are created, transactions and transactions underscore for our ags. I'm going to run Jupyter from my laptop here. Let's just start Jupyter notebook, and here we go. And I'm going to go into source module 2, and I'm going to run the backfill pipeline. So this is a notebook. I call it a pipeline, but it's really just a notebook. We're going to run it from GitHub Action as a pipeline. No, in fact, the backfill feature we won't. So the backfill feature notebook, we're only going to run on demand, and we're going to run once at the beginning. And let's go through what's going to happen when we run this. So firstly, it's going to start by importing Hopsworks and Pandas and datetime. We're going to download our historical data. So we've got credit card data available as a Parquet file. Now, many of you may not have used Parquet files before. They're very similar to CSV in that they store structured columnar data, but they do it in a columnar file format. And what that means is that it can compress data. If you have a lot of repetition of values across columns, you'll be able to efficiently compress that data. It also stores type information as well. So, if we look at the info here, we'll see that, the credit card number is recognized as an int. In this case, you can see it's an int value. It's not got spaces in a string. The provider looks like a string, and the expires looks like a string. So this is our credit card data. And let's move on and look at the profile data. So the profile data is the owner or holder of the card. We can see we've got name, sex, mail address, birth date, city, country, credit card number. And we can see, that the types are mostly identified as strings. but the birth date was pulled out as a datetime object, and that's one of the advantages of Parquet. You don't need to explicitly cast strings to date times as you do when you read from CSV files, typically with pandas. And finally, let's look at the transaction DF, which is a larger data set. And we can see it's got our unique transaction ID, TID, the credit card number, the date time, the category of the payment, the amount spent, where it happened, the city, country, and whether it was fraud or not. Because we're getting this data from the synthetic data later on, but this is our historical data, so we know whether this transaction was fraud or not. And again, we can see the typing looks okay on the data frame. So this historical data that we have, the 3 different data frames we've read from the Parquet files, well, we need to still compute features from it. So firstly, we're going to, we can take out the fraud labels and put them into a data frame here, you can see. The transaction data frame we can extract as its own data frame. And you can see we've computed our card owner age, expiry days, and activity level features. And we've done that using the library. So we've imported this CC features module from the SML package because it's in a subdirectory of where this notebook is. Then it's part of our Python path. So Python will pick it up. And that's the easiest way to include modules. Now you can also take a module and make a wheel file out of it, or a pip package and pip install it, and both of those are valid ways of packaging up your libraries. In this case, we're just making it simple and putting it as a subdirectory where the notebooks are. So I'm going to just log into Hopsworks now. I've done this previously, so my API key is cached. Otherwise I would have to paste it in here. And we did this in the first lab in case you haven't covered it, so you can get your API key from the platform. And then we're going to now compute the aggregated features, and we're just going to call the module cc_features aggregate activity by hour. And we pass in the transaction data frame and the window length, in this case 4 hours, and we get back our features for the aggregated features. So with those, we can create the feature groups, and if I jump back over to Hopsworks over here, I don't have any feature groups in here. It's quite empty. So so what we'll do is we'll just run insert at this point, and I set wait for job false. That means it's going to run the ingestion in the background. You can see it first has to upload the data, so it's uploading 100,000 or so rows, and once it's uploaded it, it's going to launch an ingestion job in the background. You can follow and track the ingestion job here. It takes about a minute to finish. But by setting wait for job false, it means I can continue in the notebook. Now we can see here that another important step you can make is you can update your feature groups with a lot of metadata. So for every single feature in this particular feature group that I created called cc_trans_fraud, we can add individual feature descriptions. Now I think in the lectures I call this CC, just transactions, but you can change the name to whatever you want for this course. So you can see here that for all of the features I've added a description, an individual description for them. And let's go back and look in the platform, and we look at our feature groups. Now we can see that this cc_trans_fraud feature group was created. And then if we look at the individual features like TID, its description is transaction ID, and category is expense category. So if we go back to the code, we can see that the category is expense category. We can get individual descriptions of the individual features, which is very useful for people who want to understand where the feature comes from, how it's computed, and how it can be used. You can put in as arbitrary descriptions in there. Okay, so now we're going to create the feature group for our aggregated features, and we're going to insert the data frame that contains those features. So again, it's around 100,000 rows, and again we can add descriptions of the features. And again, we're also doing this in the background, so we're running an ingestion job in the background. So we can go look at the previous ingestion job actually here, and we can see that the previous ingestion job took a minute and 15 seconds to finish. So now we're back at creating the second feature group, the aggregated transactions, and you can also even create a third feature group which contains just the labels. So often you might have your labels available as a separate feature group or a separate table, and we're going to store labels in the feature store in this course. You can of course find labels on external data platforms, and we did cover external feature groups in the lecture. So often you might have your labels available in a table in Snowflake, and you can create an external feature group for that table so that your labels become available within the feature store even if the data is still stored externally in Snowflake. And again, we can add descriptions for them. So let's just go back and make sure all of those exist. And yeah, we can see we have our label feature group and then the two other feature groups. Okay, so we've run this backfill feature group, and it created two feature groups. No, it actually created three feature groups. So we had also the three. Let's put in the last one to make sure we have it correct. So the last one is the name of it is the transaction fraud label feature group. Okay, here we go. There we go. Right, so that was our backfill feature pipeline, and the reason why we separated out this backfill feature pipeline from the production feature pipeline, you'll see it very quickly in a second, is let's open up the production feature pipeline here. We can see that it's actually really short in terms of code. This is the production one here, and you can see it's only, it's basically a page or so of code. So the difference between them is in this particular one, in the production feature code, we basically say we're going to create credit card transactions from the time now and for the previous 24 hours. So we're going to create so every time we run this pipeline, the timestamps or the date times for the transactions will be whatever is returned now in this Python program minus 24 hours. So if we run this with GitHub Actions once a day every 24 hours, it'll generate timestamps for that window of time. Now you can play around with this and change these values to whatever you want to. You can also play around with these parameters for how many transactions to create and how much data will be written. Let's start running it actually while we're here. And you can see here then we're creating the actual credit card data frame and the profile data frame and the transaction data frame. Same as we did in the backfill example, where we read them from the Parquet files, and now we're going to compute the features on top of them. And we're going to log into the feature store, and we're going to just write, in this case we're not going to write the aggregated features, we're just going to write the non-aggregated features. So we're going to write the transaction features themselves. Okay, so this one is running, and you can see it's finished. The job writing is going to run in the background, and we're kind of done. Right, we've written our data in here. Let's have a quick look at some of the data that arrived in here. This is our transactions feature group we can see here. And we moved the fraud column out of this actually into a separate feature group. We have a quick preview of the data here. And you can see there's quite a lot of data in here. Right? And it previews only 50 rows, I believe, and we have 11 features. You can have a look at any statistics computed over them. And you can look at the activity level. So the activity level, at the moment we just had the first write, the backfill write, but then this will get updated with, I guess, a bunch of new rows when the second job is finished. This is our production pipeline job is finished. The aggregated features we can see here. You can get a preview, statistics, the same as before. So you can have a look around and see, what for example, the location delta moving average is. Well, it's a value in the range between 0 and 1.42 with a mean of 0.27. That doesn't mean very much maybe to you, but hopefully your machine learning system can pick up on the predictive signal in that feature. That's basically it. Now, one thing that is part of the homework actually is to see, well, how much data is written. So, we can see there's features. We can figure out, how many features there are. That we look at the data type and estimate the storage requirements for them. And you can do this analytically and how many rows were written. You can find out from here. In activity, there were 106,000 rows written. And you could kind of figure out roughly how much is storage. Or an easier way to do it is just go to the file browser down here in your project settings. And if we look in at the featurestore.db, we'll see these tables that were written. So we have we've got 1, 2, 3 tables. These are the 3 different tables that we have. They're stored as hoodie files it's Parquet data. They're hoodie tables, but ultimately the data is Parquet. So we can see here that, for the transaction fraud data, we have two Parquet files, and they're 7.7 megabytes and 12.1 megabytes respectively. So it partitioned the data. And if we look at the aggregated features, you can see there's a single Parquet file of 4.8 megabytes. And for the transaction fraud label, again, we have a single Parquet file. Now, the reason why we have two Parquet files for the transaction fraud one was because our production feature store wrote this second set of second set of transactions. So if we go back to the actual feature group here and look at the activity, we can see that it's finished writing, and it wrote 71k new rows. Okay, so one of the exercises is to try and write 50 megabytes of data. So we can see that our write, and you can figure out if we go back to the write that we had in our file browser. Let's go back and look at the write here. We can see that this write happened first, and then this write happened second. So the most recent write produced 12.1 megabytes of data, and it was new data. So what you can try and do is you can try and go back to your feature pipeline here and change some of these parameters here. So you want to maybe create more transactions, and try and write roughly 50 megabytes and report to us what parameters you changed and what value you set that produced about 50 megabytes of data. Okay. So we've run both of these pipelines. We've run them as notebooks. We haven't run them in GitHub Actions. So let's have a look at the unit test, and we're in our module here. So you can see here we have this package called test_ml, and we're supposed to just run python -m pytest. And we can see two tests pass. So let's have a quick look at what those tests were. And we can go back and see them in here in GitHub. So the tests were very simple. There's a function in the synthetic data module called generate ATM withdrawal, and what it does is it takes in a credit card number, a list of cash amounts, the length of those, delta, radius, and the country code, and basically we call this function generate ATM withdrawal twice. Firstly with this set of parameters, so this is the first entry, and the second time we call it was with this set of parameters. And the expectation from the first set of parameters is that it won't raise an exception. So this data is you can say it's correct data for creating ATM withdrawals. And the second set of data is incorrect, mostly because this length here is a negative number, and it shouldn't be a negative number. So the function will pick up on this and throw an exception, because say, well, you shouldn't have a length that's less than 0. So you can one other task is to pick any function from the synthetic data or from the cc_features Python module and write a new unit test. And this is kind of the format for it. This is a nice way of passing in sample data using pytest mark parameterize. And you can copy this basic structure, put in a different method. See, we're calling synthetic data.atm generate ATM withdrawal. And you can just pick another method either from that module or from the cc_features module. Okay, so we've done all those tasks, and the homework, as I mentioned already, is to try and run a pipeline that produces about 50 megabytes of transaction data, and tell us the parameters that you have. Write a unit test for a function of your choice, and also run your GitHub action. So we haven't looked at the GitHub action, and that's the last thing we're going to do here. So let's go back here at our actions. So I wrote this one earlier. It's the fraud feature pipelines action. It's the same as we had in the first lab, pretty much. We can set on workflow dispatch so that we can run it from the user interface, and it runs on a schedule at 11 minutes past 11 every day. It installs Python 3.8.1, installs all of the libraries in the requirements.txt file. That file has been updated to include the faker library that we need here. And then finally we just run this script that we looked at earlier, which will run our production notebook. So this is the cc_features_pipeline IPython notebook. So that's it for the lab. Good luck in carrying out the different tasks. and then you can submit your homework at this particular link. And I'm looking forward to seeing you in the next lecture, which will be on training pipelines and inference pipelines. Thanks.